Hello, welcome to the online version of Math 383. We will be starting a new module over the coming weeks that is going to be focused on systems of differential equations. And the first topic of interest is going to be linear systems of differential equations. We will start off by considering some motivating examples. These are going to be drawn from the current circumstances that have moved us to an online format, and we'll be looking at models of infectious disease propagation. We'll start off with a model for interacting screening clinics. As we will see, this leads to a linear system of differential equations. We will then consider the prototypical model that is used in infectious disease propagation in a population, the SIR model. This is an acronym for susceptible, infectious, recovered. As we'll see that this model leads to a nonlinear system of differential equations. Finally, we will consider a prototypical model that is coming from mechanics, namely one of coupled oscillators, in which multiple masses, springs, and dampening elements interact, and we are interested in the collective motion. After the motivating examples, we will turn to the formulation of linear systems of differential equations, and then we will start our consideration of solution techniques by looking at the simplest case, namely of homogeneous linear systems of differential equations. Before we move on, let's introduce some acronyms for all of this, and we will say that a linear system of differential equations is an LSTE. A nonlinear one is going to be something that we preface with an N. If we have a homogeneous linear system, it's going to be a subcase, and we're going to put a lowercase h in front of it. So now let's move on to our first motivating example. Namely, we will consider the following scenario. We have two clinics that are meant to screen an incoming population. These clinics have varying capacities, one suited to higher probability of an infected individual being checked and one to lower probability, and they also have different capacity in terms of treatment. Let's start by drawing a diagram of the situation that we will be considering. The diagram will then be used in order to derive a set of equations. So we'll set this up as a table with the left-hand side for the equations, the right-hand side for a diagram. Let's draw a diagram in here. This diagram is going to be right about 4 inches wide and 5 inches high, and we'll put a grid to help us line things up. And what we have is going to be as follows. There is going to be two clinics. So let's say clinic A is the one that is suited for persons coming in with a smaller probability of infectious disease. Then there's another clinic, clinic B, that is going to be for patients with a higher probability of infectious disease. Clinic A, clinic B. So patients are coming in to be checked into each of these clinics, and they are also being discharged after being checked. And there's also a transfer of patients between clinics. So let's put some arrows down to kind of show all of these fluxes. There's incoming patients to each of the clinic. Patients are being discharged from each clinic. And there's a transfer of patients from one clinic to the other. As mentioned, the first clinic is the one that is recommended for patients in the low-risk population. So typically you'll see patients there that have a lower probability of having a disease. There's going to be, let's say, about 5 persons per hour coming in to be checked in here, and they will typically have a probability of being infected of 0.2. Then in the other clinic, we're going to have patients more likely to be infected. Let's say that there's a smaller flux of such patients, only 4 persons per hour, and the probability that they actually are infected is a bit higher, so let's make that at 0.5. Some patients get transferred from one clinic to another. Let's say on average 2 persons per hour get transferred from the clinic A to clinic B, and from the clinic B to clinic A we have a transfer of 3 persons per hour. We also have discharge of patients that have been cleared, and we'll assume that from clinic A, the one that is for the population which is at less risk, on average 6 persons per hour get discharged, while from clinic B we have on average 3 persons per hour getting discharged. Note that the values have been chosen such that the overall inflow and outflow is the same. There is 5 plus 4, 9 persons per hour coming in, 6 plus 3 persons per hour coming out, again 9. This will be changed in further models, but we call this basically a steady state model. Each of these clinics is being run at capacity, and we will assume that the capacity of clinic A is going to be, let's say 100, and the capacity of clinic B is going to be 300. And we'll draw some rectangles to kind of denote this. This one is going to be a capacity of, let's say, like we said, 100, and another larger capacity for clinic B. And the interest now is going to be to figure out from this data what the time evolution of the number of infected individuals might be in each clinic. Now, how do we go about that? Well, we recognize that what we have here is actually a specification of rates of change in the numbers of infected persons that are given by indirect information, namely by the influx of persons with certain probabilities of being infected. So now let's move over to the derivation of the mathematics that we need. Let's take away the grid and just leave the diagram. Go to the other side over here and start thinking about writing some equations for all of this. We'll set up another table. This table is now going to be a table of equations, and we'll make some initial space in here for a few items. So what do we have? Well, first off, we have the need to introduce the dependent and independent variables. Clearly, the independent variable in this case is going to be time. We are interested in following the evolution of patients as time goes on, and we're going to measure this in hours. Then the dependent variables are going to be the number of infected individuals in each one of the clinics, and let's call these dependent variables just A as a function of t and B as a function of t, and of course this is essentially something that we measure in number of persons. Let's allow for some more space over here, so to take away the units, we will assume that we know what units we're talking about, and specify that both A and B, from our point of view, are going to be functions. They are both defined on the reals, and they return real values at this point. And remember, A and B are intended to show the number of infected persons in each clinic. Now, note that not only have we ensured overall steady state in the sense that 5 plus 4, 9 persons come in both clinics and 9 persons go out, but also we have ensured steady state for each individual clinic in the sense that we have, for clinic A, let's say 5 coming in, 2 being transferred to clinic B, another 3 coming in from clinic B, and finally 6 going out. So all of that is of course going to be 0, and we are in steady state. So now, what is the rate of change? Well, let's start off with clinic A, and we're going to be coming up with a formula for the derivative A prime, namely the rate of change of infected persons in clinic A. This is going to be given by the following terms. We have 5 persons coming per hour, and the probability that one of these persons is infected is 0.2. So we have the incoming flux of 0.2 times 5. Now, we also have a incoming flux from clinic B and then an outgoing flux from clinic A to B, and also going all the way out. And we're going to have to figure out the effect of both of these fluxes upon the rate of change of infected persons in clinic A. So if A is the number of infected persons in clinic A, and clinic A has 100 person capacity, the probability of any given person being infected at some given time is going to be A over 100. Note that we have 8 persons going out of clinic A per hour, so the rate of change in this particular case is going to be the following. We're going to have 8 over 100 times A. Here you can think of the flux from A to B as denoting persons that need further screening, and the outflow from A, 6 persons per hour, at persons that actually need to be treated somewhere else, hospital for instance. From the point of view of clinic A, both of those are outfluxes, so this is going to be with a negative sign. Similarly, we are going to have an inflow into clinic A of infected individuals from clinic B, and the percentage or of the people that are in clinic B that are infected is going to be B over 300. There are 3 persons coming in, so we're going to have 3 over 300 times B as the incoming infected population. Similar considerations apply to now the rate of change for the number of infected people in clinic B, and we're just going to more rapidly go through this. B prime is going to be something that is now going to be 0.5 times 4 persons coming in per hour. Then we're going to have people coming in. These are coming in from clinic A, which, as you recall, it has a capacity of 100, and the rate at which they're coming in is 2 persons per hour. And we also are going to have people going out of clinic B. There are 300 people capacity in clinic B, and the total flux going out is about 6 persons per hour, and this is going to now close the system for this particular scenario. Let's now rewrite this to bring out the linear structure of the system. What we have here, after we look at simplification of the arithmetic, is now going to be a system of equations written out in full. It would be as follows. A prime is going to be 1 minus 0.08 times A plus 0.01 times B, while B prime is going to be 2 plus 0.02 times A minus 0.02 times B. However, we will actually be more interested in recognizing that this can also be put now in matrix form. And if you look at it, you can introduce a vector. Let's call this vector y. This vector is going to have two elements in it. These are going to be the dependent variables a and b. The vector is something which depends on t because of the dependence on t of a and b. And the rate of change of the vector y prime, is something that can be stated in terms of multiplication by a matrix. Let's call this matrix M, that multiplies y and also has some right-hand side free term which we'll call f. By investigation, you can readily look at the form written out in full and come up to the conclusion that M is going to be a 2 by 2 matrix. This matrix is going to have the following elements. Let's see, the first element here would be the coefficient that multiplies A in the first equation, and of course that's minus 0.08. Then the coefficient that multiplies B, that's 0.01. Coefficient that multiplies A in the second equation, 0.02. And the coefficient that multiplies B in the second equation, again that's 0.02, but now with a negative sign. Whereas the term f that we have over there, this is something that is going to be a vector, and this vector is something that from the above just has constant components of 1 and 2. Now recall that from our perusal of linear algebra from the past few weeks, a matrix vector product is basically a linear combination of the columns of the matrix with coefficients which are given by the components of the vector. So we interpret this relation y prime as my plus f as stating that we have the rate of change of y as being a linear combination of these columns of M. These are essentially from the point of view of the system transition probabilities for infected states. Before moving on to our second motivating example, let's actually solve this particular problem. We'll present analytical solution procedures in the course of these lessons, but for now we'll basically just use the facilities of Mixima to give us a solution that we can analyze and assess the utility of models such as this one. So let's actually come up with a solution for screening clinics model. And here again we will be separating things off, and let's put a figure in the right hand side over here. Let's say that the figure is going to be maybe 5 inches wide this time around, and in the left hand side we're actually going to introduce a maxima session in which we're going to define the model. So what does the model look like? We'll probably need a bit more space for the model, so let's reduce this to just 3 inches over here. And for the model we are going to define equations that give the rate of change. So we'll call the first equation dA. Remember, dA colon is a specification of the name of whatever follows after the colon. And the rate of change that we have is going to be given by derivative of t with respect to t, and this is now going to be given by 1 minus 8 times 100 8 times 8 divided by 100 plus b divided by 100, and that's our first equation. We have to be careful about explicitly putting in the dependence on t in this equation. That's the first equation that we will define. Then shift enter and we define our second equation, which we call db. Again, it's going to be a derivative, this time of the function b of t with respect to t. And this is now going to be given by 2 plus 2 times a divided by 100 and minus 2 times b of t divided by 100. Evaluate this, and we see that we have our system defined. After defining our system, let us find the general solution by invoking the dsolve function. We are interested in solving the equations which have been labeled dA and dB. There's two of them. We put them in brackets. We're finding two functions as the solution, again in brackets. The first function is a of t. The second function is b of t. We can find the solution. Now this is a fairly complicated solution that comes out of here. We will understand a bit later on exactly where these numbers come from. Since we're interested in qualitative behavior at this point, let us move on to adding in some instructions such that instead of displaying this general solution, we find a particular solution. And this particular solution will be obtained by considering what we would obtain from substituting initial values. Let's say that the initial number of infected patients within clinic A is 50 and that in clinic B is 200, and we will substitute these values within the general solution. Evaluating this now leads to a slightly simpler form. Substituting initial values, let's say that the initial number of infected patients within clinic A is 50 and the initial value of infected patients within clinic B is 200, values that we will substitute in the general solution. Changing this semicolon into $sign will suppress the output from the previous general solution, so we'll only see the solution from the particular solution that corresponds to those initial values. Evaluating now leads to this particular form. We're not particularly interested in the analytical form, so let's suppress this output and add on just a few more instructions that will now allow us to obtain a plot of the solution. So what we will do is we will define something that we'll call PA, and this will be the right-hand side of the particular solution, and namely its first component. And we'll also define something which we will call PB, and this will be again the right-hand side of the particular solution, its second component. $sign again to suppress the output, and what we are really interested in is just a qualitative assessment of the way that the system evolves. So we'll do a plot. Now the plot will be of PA and PB. We've defined those above, and let's say that we let time go from the initial time of 0 to 1 week out, so 7 times 24 hours. And to render the plot information a bit more useful, we'll add in an X label. This is going to be, I guess, time in hours. And then we are going to have a Y label, let's just call those A and B. And let's give a title to the plot. This is going to be titled infected per clinic. And let us label each individual plot. So set up a legend. The first one will be called A, the second one will be called B. And this is what we really want. We would like to just get this plot to be able to ascertain the evolution of this system. Evaluating this brings up a new window, and here we see that for the particular values that we've chosen from the initial values of 250, we have an evolution which shows a decrease in the number of infected persons in each clinic, and it seems like after about a week an asymptotic value is obtained for both of these. Let's just save this plot and we'll put it in our course. So this is going to be lesson 18, figure 01. We'll save it, and then coming back to our presentation here, let's just insert this image by linking it into this right hand side of the table. So we're going to get this and make it automatically change its height and having a width, let's say of 3 inches, so that it fits into the allotted space. So now we have a qualitative solution for our system. Before moving on, let's get rid of a few spelling errors here, and then go on to our next model, our next motivating example. So motivating example 2 is now going to be the susceptible, infected, recovered model. As before, let's start off first with a diagram of what we would like to then model mathematically. And the situation that we will find ourselves in is something which is typically depicted by way of a compartment diagram. The compartment diagram specification here is a reference to a way of breaking up a population into various categories. So, as before, let's draw a diagram here, make sure that it is of the appropriate size for what we need, and the way that we think about this is that there is a total population. Let's say that this total population is represented by a rectangle, and the total population is n individuals in the population. If an infection appears, what happens is that the total population gets now split up into various groups. So whereas initially the total population was indistinguishable, there was no characteristic that distinguished one individual from another, upon the appearance of an infection, what happens is that the total population now gets separated off into 3 groups. And if you think about it a bit, the first group is going to be something which corresponds to people who have not yet built up resistance, so these are susceptible to infection. And there are a number of such individuals. We will denote the number of such individuals at any given moment in time by S of t. Then there are going to be individuals who are infected and hence also infectious. They will form the second compartment. There's a number of such individuals. We will denote these by another dependent variable which we will call I of t. And finally, there is a final group. This final group is going to be of recovered individuals. In this particular context, recovered means that they are no longer infectious or susceptible, so it's a bit macabre, but recovered in this context means both those that have recovered and are living and both those that are, and also those that have actually died. And there are a number of such individuals. And we will denote these by R of t. Now there are going to be transitions between the various types of compartments. Some of the susceptible become infected. So there is going to be a transition from the susceptible compartment into the infected compartment. Subsequently, some of the infected do recover. So there's going to be a transition from the infected compartment into the recovered. We are also going to have a need to quantify the rates at which these transitions occur. So let's just say that the susceptible to infectious is something characterized by a parameter. Let's call it beta. And the infectious to recovered is characterized by another parameter, or let's call that gamma. Let's now move on to the formulation of the model. The formulation of the model is going to be a number of equations, just as we did previously. And let's just organize those equations into a table. We're going to need an equation for each one of the three dependent variables. And we will start off by consideration of the rate of change of the susceptible population. Now what happens is that there must be a contact between a susceptible individual and an infected individual in order for the disease to be transmitted. How many contacts are possible? Well, the contacts are going to be typically proportional to I times S. Of these contacts, though, there is a certain probability that the contact does lead to the transmission. Let's call this beta, as we did in the diagram. And as a result of the contact, what happens is that the susceptible population goes down. Conversely, from the point of view of the infectious population, such a contact leads to an increase in the number of infected individuals. So this now is going to appear with a positive sign in the rate of change for the infected population. From the point of view of the recovered population, what happens is that with some probability, which we will call gamma as we did in the diagram, an infected individual becomes recovered. This leads to an increase in the number of recovered individuals and a consequent decrease in the number of infected individuals. And there we have it. This is the susceptible infected recovered, or susceptible infectious recovered model that is a cornerstone of epidemiology. Now, note that this particular model is now nonlinear. It is nonlinear in the sense that we have identified three dependent variables, S, I, and R. All of these are functions of time. So S, I, and R are defined on the reals with real values. But note that they appear multiplied with one another in this particular context. So there's no way that we could put them in the form of a multiplication of a constant matrix with a vector of unknowns that would contain these variables as we did in the previous screening clinic example. Generally speaking, such nonlinear systems are much harder to solve. There are very few actual analytical solutions that allow us to obtain predictions. However, there is another way that we can do this by numerical methods. Numerical methods will be treated in detail a bit later in the course. In essence, what happens is that instead of trying to find an analytical solution, what we think about is small increments of the change in S, for instance, or change in I, are added in according to these equations. There are several methods that do this. We will use the built-in maxima functions just to show the difference in behavior of a nonlinear system with respect to a linear system, as we had in the screening clinics example. For this, let's try to fit everything into just one slide and go ahead and make a bit of space over here. And finally, start off a session of maxima now in the other pane and set up the definitions that we need. The function which will carry out the numerical solution is called RK. This is an acronym for a run-get-kutta method. And what we will be doing is we will be solving a system of equations for which we must give the rates of change. So as before, various things are grouped together by brackets. And what we have is the rate of change for the first dependent variable. Let's take beta for a moment to be 0.02. Then this gets multiplied with I. This gets then multiplied with S. That's the rate of change for the first equation. Then 0.02 gets multiplied with I and S for the second equation. We'll assume that the recovery is 0.03. That gets multiplied with I. And the final equation is just 0.03 times I. These rates of change are going to be used in order to find the time evolution of the variables S, I, and R. Let's put this in a way that is readily legible. And we will do this for the starting time from, let's say 0 out to, let's say, 100 days. We must also give the initial values at t equals 0. So let's assume that we start off with a susceptible population of 1,000, an infected population of 0, and a recovered population of 0. When carrying out a numerical solution with the RK function, we must also give the time increment at what time slices we would like to find the solution by this numerical procedure. And let's say that this occurs every 6 hours or 0.25, a quarter of a day. Now, notice that we've chosen initial values in this particular case to give a especially simple solution, because if the infected population is 0, then the rate of change would be 0 for S, the rate of change would be 0 for I, and since I is also 0, the rate of change would be 0 for R. This is typically the first thing that you try. You just want to do a sanity check to see that you got the formulation correct before you try more interesting scenarios. Let's give a name to this solution, and we'll call this solution let's just call it S for now. We're not interested in the output, so we'll put a $sign there, and after that we will just try to construct a plot. So let's do a plot instruction here, plot 2D, and the way that this works is that you invoke this function, plot 2D. Again, it's not going to produce any output, what we would like to do is to do a plot which is a plot now not of a continuous line as it was previously, but of a number of discrete points, and we will construct these points by making a list. The list that we will make is as follows. We will make a list of the following. There's going to be the list, and the first element of that list is going to be the time values. The next element in that list is going to be the S values, and we are going to get this list from the solution which has been denoted by S. If we evaluate this, a solution pops up. Now, as expected, there is no change in the number of susceptible individuals. We just see a line. So this is in conformance with our guess, and we can now start looking at more interesting scenarios. But first off, let's make sure the plot is labeled in a more appropriate fashion. So we have an X label, which in this context is days, then a Y label, which for now is the number of susceptible individuals, and the overall title of the plot, let's call that infection propagation. So with this in place, we are now in a position to, let's make sure we have the syntax here correctly. So we are in a position to actually modify some of the values. And let's say that instead of 1,000, we have 999, one infected individual, and let's see what happens. We will start now by doing a number of numerical experiments. Let's make the time increment a bit smaller, and let's get hourly forecast. So that's 1/24th of a day. If we now execute this after a bit of time, what we have is the following plot of the susceptible population. Notice that from 999, very quickly we drop down all the way to 0. Basically, this is predicting that everybody becomes affected within a matter of hours. This is presumably due to a large infectious transmission rate, the beta parameter. So now let's look at what happens as we modify the values of that parameter. A tenfold decrease in the efficacy of transmission of the disease from 0.02 to 2,000ths now will lead to the following evolution. Notice that again, all of the population becomes infected, this time on a slower time horizon. Going back, if we decrease the efficacy of infection again by a factor of 10, we get another prediction. This time the number of susceptible individuals again goes down to 0. Everybody gets the infection eventually, but over a much longer time period. This is essentially what is referred as flattening the curve. Instead of everybody becoming infected very quickly and thereby overwhelming the capabilities of the health system, infections occur spread out over a larger period of time. Let's work on the plot a bit and get a representation of the infected and recovered population also. Skipping over some of the details, which you can just pick up from the posted slides, here are the results for a scenario that goes out to 180 days. And notice that we have a peak of infected at around 575 or something of that nature. Let's see what happens if we decrease the infectiousness yet again. After decreasing the infectiousness rate by a factor of 2, notice that the infected population has dropped to roughly 50% of the previous scenario, and it occurs much further out at 110 days, giving much more time for preparation for the expected large number of infected individuals. Another reduction by a factor of 2 now leads within the 180-day time horizon to an extremely small number of infected individuals, much less than 100. This is really the intent of social distancing, and note the effectiveness of introducing a certain amount of reduction of social interactions upon the overall number of infected individuals. Qualitatively, what happens is that there's exponential growth in these equations, as we'll see when we look at the detailed mathematics of the system, and small reductions of the infectiousness rate parameter, beta, can lead to marked changes in the overall infected population. Let's now move into our third motivating example. This motivating example is coming from mechanics, namely coupled oscillators. And here the significant features of this example is that we can consider a simple modification that transitions from a linear system to a nonlinear system, and we can investigate the extremely marked difference between the behavior of the linear system by comparison to the nonlinear system. As before, we will start with a diagram and then transform that diagram into equations. The diagram that we're going to be interested this time around is going to be that of two oscillators, two masses that are connected by both springs and dampeners. So here is a diagram of the system that we will be considering. There are 2 point masses. These are M1 and M2. These are connected to one another through spring dampener elements, and we will denote by y1 the displacement from the equilibrium position. So y1 equals 0 corresponds to the equilibrium position, and y2 is going to be the displacement from the equilibrium position of the second point mass. The springs are characterized by spring stiffnesses K1 and K2, and the dampeners are characterized by a dampening or friction coefficient C1 for the first one and C2 for the second one. Now we will assume that the dampeners have essentially zero length, such that the distance y2 minus y1 actually gives me the elongation of spring 2 with respect to its equilibrium length. As before, we will now go ahead and put this system into the form of a system of differential equations. So let's go ahead and put in a table. This table is going to contain our equations, and our first equation is going to be for the rate of change in time of the first point mass, y1. Now if you think about it a bit, y1 is going to be the rate of change of the position, so this is a velocity. In order to write the dynamics equations, we are going to consider the second derivative. That's going to be the acceleration, and mass 1 times acceleration is going to be the rate of change of momentum. The rate of change of momentum by Newton's law is going to be given by the sum of forces that act on this particular spring. Now we're going to be taking a downward pointing y-axis, so the forces that have to be considered are as follows. Let's assume that there is some gravitational acceleration. That gravitational acceleration is going to be m1g. That's the gravitational force that acts upon this. After that, we will have the following forces. There's going to be a force exerted by spring 1 upon mass 1. Now when y1 is positive, so it's moved away from its equilibrium position, that means a lengthening of the spring. The spring is going to exert a force in the opposite direction, so we have minus k1 times y1. That's the elastic restoring force. We're also going to have now a friction force. This friction force is going to be proportional to the velocity, so it's minus c1 and now y1 prime. Besides the forces exerted by dampener 1 and spring 1 upon mass 1, there are also going to be forces exerted by spring 2 upon mass 1. And now the extension of spring 2 with respect to its equilibrium position is going to be the difference between y2 and y1. Notice that when y2 grows, this spring, namely spring 2, extends its length, but if y1 increases, then spring 2 decreases its length. The constant, the elastic spring constant in this case, is k2. And we have now completed all of the forces that act upon mass 1. We repeat this process for mass 2. So mass 2 times y2 double prime, the acceleration, is going to be given by the gravitational force, and we are now going to have an effect of the elastic force. This is going to be minus k2 times, what is it going to be this time? Well, we have again to take into account the extension, y2 minus y1. We're going to have a drag force from the dampener. This is going to be c2 times y2 prime. As a final check, we have to look at the signs and notice that in the second equation, when y2 is greater than y1, that's an extension of spring 2. That extension of spring 2 tends to give a restoring force in the negative direction, so this sign over here is correct in the second equation. But when the second spring is extended, that force on mass 1 tends to pull it further down, so the force that we have here has to have a positive sign. Notice that as written here, the system is linear in the sense that the unknown dependent variables y1 and y2 do not appear multiplied with one another anywhere within the system. So this could actually be put in the form of a matrix vector product if we would like to do that. However, what we will do is to highlight the difference between linear and nonlinear behavior by first solving this system by numeric means, even though an analytical solution is available. Now, in order to do this, we first have to transform these two differential equations of second order into a system of first order differential equations that can be solved by the numerical Runge-Kutta procedure. This is a very simple procedure in which we just introduce a notation for the velocity. Let's say the velocity of mass 1, which is y1 prime, is denoted by v1, and the same for mass 2. As soon as you do that, then you can rewrite the overall system of two differential equations of second order as a system of four equations of first order. So now let's write this out in a form that can be solved numerically. This is the coding. It's not all that important at this point. We are setting an initial condition here in which the velocity of mass 1 is 0, the velocity of mass 2 is 1, and the positions are 0, 0, meaning that the initial state is that both point masses are at equilibrium. Mass 1 is stationary, but mass 2 is given an initial velocity of 1. Remember, this is in the downward direction. And we're going to integrate the system forward in time for 1 unit of time. After carrying out the integration, this is what we see as our result. The representation we're doing here is known as a phase portrait. This does not show the 4 variables that we have, the 4 dependent variables, namely positions y1, y2, and velocities v1 and v2 as functions of time. Rather, what we're doing is that we're showing for point mass 1 the velocity as a function of its position. So notice that this blue curve that corresponds to point mass 1 is starting off from 0, 0, meaning 0 velocity, 0 position at equilibrium, and then it is being accelerated by the effect of the second mass, the red curve, which was given an initial velocity of 1 at its initial position of 0. This type of phase portrait is very illuminating in terms of getting an appreciation of the richness of behavior that can occur in these systems of differential equations, such as arise from coupled oscillators. Let's push this integration out forward in time. Right now we're integrating up to 1, but let's push the integration time out all the way to 10. Notice what is happening now. As we have a larger integration time, the point masses are describing complicated trajectories in this phase portrait space, as it's called. Pushing the integration time out to 100, you can see even more complicated behavior. We can get a feeling for the overall behavior of the system if we consider modifications of the parameters as we look at the phase portraits. For instance, notice here that it kind of seems that trajectories are going and converging onto 0. This is the effect of dissipation, which is slowly taking away energy from the oscillation of the system. Right now, the dissipation as given by the C1 and C2 coefficients is very small. It's just 1 over 100. Let's see what happens over the same integration time if we now make the dissipation 100 times larger. After running the code, getting the solution by numerical means, notice that what has happened is that the system very rapidly goes to negligible velocity and negligible displacement. The dissipation is dampening down the system quite significantly. Conversely, if we take away the dissipation completely, what we notice is that the system does not lose energy, and this kind of behavior is typical. What is happening is that the two oscillators are tending to move in something which would be enveloped in an ellipse. This is actually a reflection of the conservation of energy in this case. Since there is no dissipation, typically the trajectories will always stay within an ellipse that corresponds to the balance of kinetic and potential energy. Now, try to remember this graph as we now move to a slightly, well, not a slightly, but actually a markedly different system in which we will artificially introduce a nonlinearity in the system. We will assume now that we do not have a constant spring stiffness, but actually that the spring stiffness depends on the elongation. Let's carry out that change in the code and look at the behavior of the system in this phase space. Now look at the behavior. What we've done is we've cubed the y1, so this can be interpreted as saying that the stiffness somehow varies with the square of y1. And the effect upon the phase portrait, the way that mass 1 velocity versus mass 1 position, and the same for mass 2, appears now, is remarkably different with respect to the previous graph. Such qualitatively different behaviors are the essence of the theoretical development that we will now start for systems of differential equations. And understanding this kind of behavior is crucial, since most applications of differential equations actually are from coupled systems, such as we've seen in the motivating examples within this lesson. Before Before we move on to the theory, here are the 4 plots that we've constructed. Remember, the first one that we did was for slightly damped motion. The next one was for strongly damped motion. And then we continued with no dampening and finished off with nonlinear springs. You're of course welcome, and it's strongly recommended for you to try modifying the parameters in the code that is available within the slides that we have here on your own computers to get a feeling for the behavior of such systems. But now let's move on to our first foray into the theory, and we will consider linear systems of differential equations. Now, as we've been exposed to in our study of linear algebra, essentially what is happening here is that we will be introducing a vector of unknowns. These are the dependent variables. And we will denote these by a bold-faced y. This is going to be a function. It's going to have a single argument, typically time, and this function is going to return n components. The components within y are just going to be elements of the vector, and these will be denoted as y1 to yn. They are functions of time, each and one of them, and we will be using the convention that boldface is the vector while normal face with a subscript is a particular component. And as you've been already now quite familiar with, the rate of time of change of this vector can be expressed as a linear dependence if there is some matrix A which multiplies the vector y. Now, the matrix A, in order for the system to be linear, cannot depend on y itself, but it can depend on t. And in addition to the linear dependence of the derivative y prime on y, we might also have some forcing term rendering the system inhomogeneous, and let's call that f of t. This is the general explicit form of a linear system of differential equations. Of course, we can add on an initial condition. Y at some time, typically taken to be 0, is given, and it can be, let's say some constants k, that's one notation, or another notation which is very often used is just y boldface sub 0, denoting the vector of initial conditions. The interesting thing now is to think about how we would ascertain the existence of solutions, but we kind of understand how this would work out from our knowledge of just scalar differential equations. Remember that if the slope field was continuous, then we were ensured of the existence of a solution. This also holds in the case of systems of differential equations, and we have the following theorem. To discuss the theorem, it is convenient to also introduce a single notation. I'll just say capital F for the entire right-hand side term, and this is a function of t and y. And the theorem that we have is as follows. If we have A and F continuous. So A, which is a function defined on R, namely time, and it gives us back n by n coefficients organized as a matrix, and F, which is a function defined on time and gives us back n forcing functions for each individual component of the vector of dependent variables, the unknowns, are continuous on some open interval, let's call it AB, that contains the initial condition, then the initial value problem that we defined above, so let's call this initial value problem, has a unique solution on AB. This is similar to what we had for scalar differential equations. Remember that in the case of scalar differential equations, to affirm uniqueness, we also had to have a bit more. We had to have differentiability with respect to the unknown variable y. But in the case of a linear system, this is self-evidently true, since f depends linearly on y, and that differentiability is ensured. So continuity of a of t and f of t will ensure uniqueness. Note also that if we have an nth order differential equation, let's say that we have an nth order differential equation for the dependent variable z, such as z differentiated n times plus some function, let's say p1 times z differentiated n minus 1 times, plus so on, all the way to some p sub n minus 1 z differentiated once, plus p sub 0 z undifferentiated, equal minus g of t. Then this nth order differential equation is essentially equivalent to the system that we've considered above, and this is rather easy to show. All we have to do is introduce notation, and the notation that we would introduce is of the following nature. We would have that z is denoted by y1, then z prime would be y2, of course this is equal to y1 prime, and so on until we would come to z differentiated n minus 1 times, which we would denote by yn, and of course this would be yn minus 1 differentiated once. From the above we see that we get first order differential equations from y1 prime is y2 and so on, and the initial equation that we started off from is just going to be something that we can write as yn prime. Remember, this is z differentiated n times, is now just going to be equal to, from the above, minus g minus p sub 1 of what the z differentiated n minus 1 times, but that's just yn, and you keep on going all the way to p sub 0, and that's going to multiply y1. So that is now going to be the final equation that we have, and we have here n minus 1 equations. Here is the nth equation. We've got the system again. And just to correct the typo, sorry about that, this is of course Pn over here, P1, P2, Pn minus 1 to Pn, and this one over here of course is also Pn. And things now are correctly written out. Let's now move on to the basic theory, and we will start by looking at the first part of this theory, namely homogeneous systems of linear differential equations. Such a homogeneous system is going to be characterized by the fact that we have the vector y prime, this is the vector rate of change, is going to be given by some matrix A times y, but the f term, the right hand side term, is 0. So this is a homogeneous system of differential equations, linear system of Ds, or HLSD. Now clearly one solution is obvious. If we have y equals 0, then the equation is satisfied. Of course, this trivial solution is not of interest. Y equals the vector 0 is a trivial solution, and we are going to be interested actually in solutions that are non-zero. The theory that we build up now is just going to be a generalization of that we've already encountered for second-order differential equations, and it's strongly based on linear algebra. Let us consider a set of solutions to the homogeneous LSD. Namely, this set is going to contain one vector of solutions y1 and another one y2, all the way to a final one which is yn. From these we can form a linear combination. The linear combination would be some y, which would be a scalar c1 that amplifies the direction given by y1, plus another scalar c2 that multiplies y2, all the way of course to the final one yn multiplied by cn. Now, if any solution of our system y prime is a y can be written as the linear combination above, this linear combination we have here, then we call S a fundamental set of solutions. So this is an important concept, that of a fundamental set of solutions, and we have an associated theorem here that tells us the following, namely that this set of solutions S with these n members is a fundamental set of solutions if and only if S is linearly independent. And of course, this is exactly the situation that we encountered previously with second-order differential equations, the particular case when n was